Hey guys, welcome to the Pump System Basics course and this introduction video. In this video we're going to outline what to expect from the video series as well as define the goals for the course itself. We're going to start off with this introduction and then we're going to go through the basic pump principles, we're going to go through basic pump types, pump components, how to read a pump curve, performance data, measurements and instrumentation used in pumping systems, monitoring pump performance, valves, isolation and control valves, system head curves, electric motors, force, work, energy, power and efficiency calculations, and we're going to end off with cavitation. The purpose of this course is to explain the role played by each component in a pumping system and how pipes, valves as well as pumps need to operate in order to achieve the best efficiency. These videos will consist of various case studies, guidelines, pump curves, and checklists to help you with your day-to-day work. The case studies will consist of bulk water and wastewater relevant examples. The guidelines will assist you with developing of specifications and tender documentation. The pump curves will help you get access to all the links and all the necessary libraries that you can draw information from. And the checklists will help you develop easy to complete data sheets as well as inspection hold point checks that you can do the next time you're on site and inspecting. Mr. Elon Musk, the CEO of Tesla and SpaceX, who was actually born in South Africa, is known for embarking on ambitious engineering projects. And I came across an interview in a news article he did a couple of years ago, and it actually quite surprised me. He had recently just made all his Tesla patents available to everyone and to the public for download. And he was questioned and asked why he was giving this information and these intellectual properties away. And his answer was quite intriguing. He said, if we're all on a ship together and there's holes in the ship and we're bailing water out and we have a great design for a bucket, we should probably share this bucket design, because we're all going to sink. And this is something that got me thinking a couple of years ago with regards to how we can share information and accelerate learning and create new platforms for our social media millennials for easy consumption of knowledge. Much like hours and hours can be spent on various social media platforms absorbing media, learning and future education systems should take on similar media formats to accelerate learning. Pump systems. Pump systems deliver services, they require maintenance and consume lots of energy. So we've got to take things into account such as efficiency, capacity, flow rate, pressure and cost to achieve a specific goal. So why are we here? First off, we need to admit that we have a problem. And secondly, embark on transferring skills and lessons learned. This course is intended to inspire change. Each one of us can make a difference. We can accelerate our own learning and find better ways to apply our skills base. We can embark on organizational culture changes, and we need to break down the silos between government, industry, interdepartmental silos, as well as multidisciplinary silos between the different engineering disciplines. On the right, we've got an illustration that I felt was very apt, and it says there, are we too busy to innovate? And this is what happens. We embark on short-term goals, and we make sure that we achieve those goals, but we don't really think about the long-term prospects and the most efficient way of doing that, and we tend to repeat our same mistakes again and again. One of my favorite analogies is a car and the car dashboard and how that information and that system relates to a pump and a pump system and the associated equipment that we use. So in front of us we have a simple car dashboard display. It shows you various instruments. We have the speed, kilometers per hour or miles per hour in the middle. On the left hand side we've got the RPM that the engine is accelerating or running at. On the right hand side we've got a fuel gauge which indicates empty or full. We've got the temperature which ranges from cold to hot, and we've got a range in the middle that gives us an indication of how many miles or kilometers we've got left on that tank. Now, can you possibly imagine if this information was not available to you in your car. If you were forced to drive a car with no indication of the speed, no indication of how fast the engine was running, or how much fuel you had left in the tank. These are all instruments that you taught to read when you do your learner's and your driver's test at a young age. But somehow we tend to neglect the associated equipment and instruments in a pumping system. So in your car, if none of this information was provided, I can assure you that within a due course, you will receive a number of traffic fines. You will run out of fuel. You will overheat. You'll change gears very inefficiently at very incorrect RPMs and nowhere near the efficient changeover RPMs. And these are all things that you can't do effectively without the correct information to assist you. And this is exactly the same in a pumping system. But yet I find that many industries tend to install very large equipment and machinery, yet we don't always install every single instrument that is required. If we wouldn't dare drive our car without all this information and these instrument readouts, why do we in the industry then allow large equipment and machines to be installed without every single piece of instrumentation working and available at all times? And this is something that is extremely important to me and something that we want to get across in this course itself. We're not here to discuss pumps and motors. We're here to discuss the entire pump system and how every single component interacts and why each one is so important to achieve the goals that we want to achieve. The importance of associated equipment. Arguably the most important instrument in a pumping system is a pressure gauge. All instruments, as we've just discussed, are extremely important, and having them at your disposal is paramount to ensuring that you have an effectively run and maintained system. You need to know where your current set points are. You need to know how things are running and where they should be running in terms of best efficiency and their intended design. And more importantly, you need to ensure that your equipment can be predicted when maintenance needs to happen, and things can be stopped when they need to be attended to, and things can be prevented, and unnecessarily breakages, stoppages, or breakdowns can be avoided. So some simple addition and subtraction can change you into an effective pump specialist by simply reading the instruments that are talking to you. Exactly the same as being able to decipher the car dashboard instrumentation, and that's become second nature to you over many years. In a pump system, it should be exactly the same. You should be able to read pressure gauges, flow meters, amp meters, and other, and you should immediately be able to tell from looking at the O&M equipment data sheets and the pump curves exactly where and how that system is operating, and if it is according to the design and the original intention. Whether you are a plant operator, a civil engineer, mechanical or electrical engineer, you're all working towards a common goal when dealing with pump systems. You need to ensure that the system has properly been designed, proper operation and procedures follow, and proper maintenance is done, corrective and preventative. The system is only as good as its weakest link. Did you know the pump is the second most common piece of machinery in the world today, consuming a total of 25% of all electrical energy produced? This is massive, and energy in is equal to energy out. Efficiency is key, and even a change in 1% or 0.1% can have a massive impact on the amount of energy that we require on a day-to-day basis in the world. Municipal water cycle. In order to simplify a municipal water cycle, we've included an illustration to show you the various steps in the network from start to end. So on the left-hand side, we have a dam or reservoir or some capture mechanism. This collects rain and other river water. This then flows through to bulk water treatment plants. Now these bulk water treatment plants purify and treat the water for consumption, meeting various SANS and Blue Drop standards in the world. It then gets pumped through to reservoirs. This is normally gravity fed or pumped depending on the network and the available land surrounding it. It then goes through to minor distribution reservoirs, and then it gets pumped into schools, households, hospitals, industries, and residential areas. This is clean drinking water. From those industries, schools, hospitals, and residential and other, it then becomes sewage, and that sewage is then normally captured via gravity to normal collection points. Those collection points and pump stations then lift and boost the sewage up to levels that it can flow in by gravity again, all the way through to a wastewater treatment works, where it is then either treated for reuse and it can be pushed back into the network for uses at golf courses and other irrigation consumers. The excess wastewater that's treated, that is not consumed or reused within the network, then flows into a river and into our seas, where it then evaporates and later it becomes rain and starts the cycle again. Therefore, in any municipal environment, you can have departments working in different aspects along this cycle. So for instance, you'll have a bulk water or drinking water department that deals with the dams and the water treatment plants. You've then got a reticulation pipeline systems department that would deal with all the pipe work in between the households, the treatment plants, and the pump stations. You would then have pump stations included in a reticulation type department. Then wastewater treatment plants would normally fall under a completely different department, as they meet different standards. They're normally green drop type international standards. And then you would have a department that manages the demand of the entire network, and ensuring that what's coming in is going out, in looking at the losses in the pipe network, evaporation, and how to effectively use the most water possible and have the least amount of wastage. So, course outcomes. Teamwork is what we are trying to expedite. We want technicians, we want process controllers, we want operators, we want electrical engineers, mechanical engineers, management, and even civil engineers to all be talking the same language. We're all trying to achieve the same goals and have the same outcomes, yet we all do it with a slightly different perspective on the job, and exactly what we're trying to achieve is sometimes just done in a different way. And this needs to be communicated properly. One of the biggest problems that I've found over the last 10 years is that communication between these multi-engineering disciplines is 9 times out of 10 what causes the problems. This brings us to the end of the introductory video. I hope you've enjoyed it. I hope you look forward to the rest of the series that is following. We have certainly put a lot of time and effort into it, and please, we're by no means experts in the industry, and if there is anything you would like to know, anything you want us to emphasize or discuss more, or if you can add value at any point to these courses, you are welcome to get hold of us and drop us an email, and we can constantly update this so that we keep it relevant and keep on learning and keep on adding additional modules and volumes. Thank you and enjoy.